In this little video, I'd like to talk to you about several things. The first one is what's in an array when you first define it. And if you look at my little program here, I've done a couple of things. The first one is I've declared a constant that tells me the array size. I suggest you do this, that way you don't have to hard code numbers in when you're using arrays. That's going to come in real handy later on when we do functions using arrays. So I've got my constant. On line 9, I declare my array, which if you visualize it, it's going to hold 5 integers. Okay, no big deal yet. You should already be comfortable with that. But what's in that array at this point? One way to find out is just to use a loop and print out the array. And that's what I'm doing right here. So let's hit Control F5 and run this thing. And we see that in slot 0, we've got this junk number up here. We've got a junk value in slot 1, slot 2, slot 3, slot 4. Now they all happen to be the same number. That's just because the operating system picked that number to stick in there. But the important thing to realize is they're just junk. There's no special value in there for us. Now another way we could see what's in the array is to use the debugger. So I'm going to come over here and I'm going to set a breakpoint on line 11. I'm going to start the debugger by pressing F5. That comes up and now the debugger's going. And I've got my watch window down here that you can see. And so I'm going to click here and I'm just going to type in nums, the name of my array. Now this is pretty cool. Look what it's telling us. There's those junk values that we saw before. It also tells us that it's an array of integers with 5 things in it. That's out here under the type column. If you look at this right here, this little X stands for hexadecimal. So this number right here is the address of nums in RAM. Now that's in base 16. You don't have to worry about that right now. If you end up taking the Computer Science 2425 course, though, you'll get into that. This is where the array is located in RAM. And something else about this debugger, it'll display it like this, or I can click this little arrow, and it'll show me each individual slot. I'm telling you that comes in handy when you're dealing with arrays. So if I step through my code now by hitting F10, it printed out the first value, and I look over here at my output screen and there it is. If I go back to here and hit F10 again, it's printed out the second one, and so on. Okay, so I can see what's in the array. Let me stop the debugger up here, and we'll take our breakpoint off for a second. So the question comes up, if all I've got is junk values in my array, how do I get good values in there? And one way is to initialize the array when you define it. Here's one way of doing that. Now I'm going to fully initialize the array here. So I put equals and I use curly braces. And let's say I want the value 10 in slot 0, and then 20, and then 30, and then 40, and then 50. This is called initializing the array, and so when we print it out now by Control F5, we've initialized the array to certain values. Now I don't have to initialize the whole thing. I could just say, all right, I want to initialize, say, the first 3 things here. And you have to ask yourself, well, then what's in slot 3 and 4? In other words, the 4th and 5th elements. Again, we can just print the array out and see. That's a fast way of doing it. Or we could use the debugger again. And notice now, the junk value in slot 3 and 4 is 0. Okay, that's different from what it was before. But the first 3 values in the array are initialized to what we wanted them to be. So what's the takeaway of that? You can initialize an array fully, which means you tell the compiler what to put in each slot, or you can initialize an array partially, like I did here on line 9. And it starts with the first element, so I couldn't say, well, I want 10, 20, and 30 to be the last 3 elements in the array, because the compiler won't let me do that. The last thing I'd like to talk to you about in this short little video is, in the text it talks about there's no bounds checking with arrays. Well, what does that mean? Well, here's an example. Let's say I change my loop up to say plus 12. So this is going to print out my array. We'll go ahead and put the 40 and 50 back here. So this is going to print the 10, 20, 30, 40, 50. And then what? It says go 12 integers beyond what the array is. Okay, surely the compiler will say, hey, Ladley, you can't do that. And so let's make sure that it will. Oh, man. The compiler goes, okay, I'll print out those values for you. What's going on here? This is weird. It printed out my 5 in the array, but there is no slot 5 or 6 or 7 or 8 or 9 or 10 or 16 for that matter. But it's printing out what? Using this little drawing right here might help you see what's going on. I've got nums, that's my array, and the indexes or slot numbers for that array are in blue down below. So I've really got slot 0, 1, 2, 3, 4. Now that's my array. So my array really stops right there. But RAM doesn't. RAM keeps on going past the array. So when you tell it to print out slot 5, for instance, well, you've gone past the boundary of the array, but the compiler doesn't warn you about it. It'll just go ahead and do it for you. Notice my program didn't crash. It just printed out whatever junk values or possibly non-junk values came after that array. If you told it to print out 1,000 numbers, you're going to get 1,000 numbers even though the array only holds 5. So that's what the textbook is talking about when it says there is no bounds checking in C++. Now Java and some other languages do bounds checking for you, and that helps. That's why when our program ran, slot 16, even though it's not in the array, it's where it would be in the array if we had declared an array that big. Oh, but it gets worse. Now what we just saw was an example of printing out values. What happens if we were storing values? Okay, let's modify the code up here a little bit. Now notice something. I'm using X as a loop counter up here, and I'm using X as a loop counter down here, but the scope of this X is only inside this loop. The scope of this X is only inside this loop. So they're really two different X's even though they have the same name. Okay, so now I'm going to store some values into my array. So I'll say nums X equals X times 100. In other words, when X is 0, in slot 0, I'll store 0. When X is 1, in slot 1, I'll store 100. In slot 2, it'll be 200, and so on. Now remember, though, I've only got 5 slots in the array. Now what's going to happen? Let's see. Okay. Did it do what we thought it was going to do? Well, it worked for slot 0, 1, 2, 3, 4, 5. But how about the things beyond the array? Y'all, I'm storing values into RAM, and I don't even know what's in the RAM to start with. And then on top of that, my program crashes because I've exceeded the array boundaries and trashed something out that I shouldn't. So let's abort. Let's get out of here. Let's declare some variables up here. And we'll make these negative numbers just so that we can see what's going on easier. Value 2. We'll say negative 10. Negative, 20? And then we'll run this. Crashes again. It stores values in there, but did anything happen to our variables? Well, let's go back and see. Let's get out of here. Let's debug it this time and set a watch or two. So I'm going to set a breakpoint. I'll hit F5. It comes back, and I want to watch nums here. Now see, this is the junk values again because I haven't initialized it yet. That doesn't occur until line 10. And I also want to set a watch on value 1, value 2, and see if I can spell value 3. And notice those are junk values too, because why? Line 9 has not occurred yet. See my little yellow arrow there? So now then when I push F10, notice that value 1, value 2, value 3 all changed because they just got initialized. And they're the values that we thought they would be. And then the next line, my array gets initialized. And I can click this little arrow and you can see the individual slots in my array. So far, so good. All right, and now I'm going to start stepping through the loop, and I'll set a watch on X down here also. So X is a junk value. Why? Because we haven't stored the 0 into the X yet on line 12. But as soon as I hit F10, notice X goes to 0 because that's the first part of a for loop. And since X is less than the array size, which is 5, plus 12, in other words, X is less than 17, it stores a value into the array. Now notice it stored a 0, like it was supposed to. It left the other values alone because we're not there yet. X goes to 1. What should happen? It should store a 1 times 100 into the next slot. It does. We keep stepping through the array. And now then that for loop, if we were just doing the array, should end right there. But we keep going. Notice X is 5. Doesn't look like anything bad has happened yet, although we know that it did. Keep an eye on value 1, 2, and 3 down there. Uh-oh. Look what happened to value 3. It got something stored in it that we didn't expect. In other words, we're trashing out the other variables in our program. Let's keep going. F10. Keep an eye on value 2 now. It just got trashed out. Notice X is 10. So what just got stored? 10 times 100, which is 1,000. We just trashed out value 2. We keep going. F10. And now value 1 just got trashed out. We're going past the array boundaries. You'd have to be in a more advanced course to realize why variables we declared before the array are the ones getting trashed out. And just a fast explanation is just because we declared them first doesn't mean that's where they are in RAM. So these variables are actually in RAM past the array. That's why they're getting trashed out, just like our little drawing back there in Paint indicated that they would. Okay, so what's the moral of the story? There's actually a couple. First of all, you, the programmer, have to keep track of where the array boundaries are. The compiler won't. It'll go, okay, if that's really what you want to do, you're the programmer. I'll trash out stuff if you want me to, or I'll print things in an array that really doesn't exist if you want me to. The second part is if you are writing to RAM, if you're storing stuff, you're trashing out memory that should not be trashed out. So you have to keep track of where those array boundaries are. There is one last thing I thought of. Let's take this loop out. And let's just print out, let's take this loop out even. And all I want to do is just say cout. I'm sending this to cout, just nums. We'll even make it like this. Now see, when you first start programming, you might think, well, I can just print out nums using my array name. And shouldn't that print all the values? Let's see what it does. Now look at this. This is printing out OOAFF. This is hexadecimal, base 16. And in base 16, we use letters to stand for some numbers. This is the address of where that array is in RAM. Now that's worth repeating. When I just use the array name, I mean the address of the first element in the array. That's a real important concept to get. So right here, nums means the address in RAM. To prove that, let's set a breakpoint right here and hit F5, start the debugger. And look right here. This is saying 00BBFB38. That's the address in RAM. Now watch what prints out. The same thing. Let's see if I can get it down here where it'll show better. Notice this address that just printed out is the same one that's in the debugger. And notice something else. It's a different address from what it was before. Okay, let's stop this debugger. Now remember this ended in B38. Keep that in mind just a second. We'll run this again. Okay, notice this address. Totally different. And when I push F10 up here, we've got a brand new location in RAM. What does that tell you? Think about that. This is telling you something about your program and where it loads into memory. Okay, that's it for this video. If you can't figure out what this is telling you, get with me.